Hey guys, how's it going? In this video, I want to go through LeetCode number 208, implement Trie. It's also called Prefix Trie. This question was asked by this company, Google, Amazon, Twitter, Pinterest, and Microsoft. Prefix Trie is one of the is a tree data structure and used to efficiently store and retrieve keys in a data set of strings. There are many different applications. So it was used in autocomplete, spell check, IT routing, predictive text, solving word games. And we didn't write 4 functions for the implementation. The try function initializes the try object. The insert function inserts a string of the words into the try system. And then the Boolean, this search function which will return a Boolean, and it will return true if the string is in the try, and that means the word has been entered before, and false otherwise. And another function is named stars with, and we input the prefix to it, and then we return a Boolean, and returns a true if there is a previously inserted word, a string words that has the prefix of the input argument, and false otherwise. So let's take a look at some example. The try, so we initialize the try object, and then we insert the word apple, and then the function what it does. So this function we need to write. This is function, one of the functions that we need to write. Also we need to write the try function as well. The search function also is another function that we need to write, and we will search the keyword, search the word apple, because the word apple has been previously inserted. That's why when we search for it, it returns true. And when we search the word app, and it returns false because the word app has not been previously inserted. However, if we search for the prefix app, that will return a true because app is a prefix of the word apple. And then if we insert the word app, when we search for it, we will return a true. I'm going to walk through two implementation to see how this works. Let's take a look at the code. And we can, in the init function, we can just put in the word list to it. So this attribute will be attached to this object each time when we initialize this try object. And then if we put in the keyword, if we put in the word, insert to it, if the word is not already in the word list, we will just append to it. So essentially, this word list will keep track of all the word that has been previously inserted, and it takes a big O of 1 for time complexity for the appending, and the checking, because we're checking on the set, we converted the list to a set, so the checking takes a time complexity of big O of 1 as well. And then the searching is pretty easy. Just look for the specific word to see if already in this word list, just so that we can know that has the word been previously inserted to it or not. And the time complexity for this one is also the big O of 1, because we are just looking at the set. And for the stars with definition or function, we look through all the word that has been inserted previously by using this for loop. So it takes the big O of the number of word that has been previously inserted in the appended to the word list. If we found this word, by FAANG, I mean if we look at the prefix number of, the length of the prefix number of character. So this one basically look at the first few character of the word that we found. If that is the same as prefix, and it will return a true, otherwise return a false. So it's pretty straightforward implementation, but in terms of performance, it's not great compared to the prefix tree, the trie data structure, because we're just using an array. And a slightly modified solution will be, instead of using a list, we can use a set. And some modification on this method. Previously, we have a append method, but for the set data structure, we just have the add method to append the new word to the set. And the search statement, the search function, and also starts with a function. They are essentially the same. And we gained a slightly better in performance for the time, and slightly worse performance for the space complexity. So a little bit trade-off here between the time complexity and also the space complexity. The next one we will go through is the trie data structure. And I'm going to walk through the implementation, but the theory behind it, I think there's a YouTube video that goes through it pretty well. I recommend watch this video before going through the notes. However, if you're going to the code, however, the implementation on this YouTube video was on Java. In here, we are doing on Python. So first thing, we create a separate class named nodes, and each node has some child, and the initialization is have the 26, the size of 26 of a list as a child, because 26 being 26 English letter and all lowercase. That's why we only need 26. And initially, all of the value being none. And is and is a Boolean attribute, and true being that's the last character of the word, and false mean otherwise. So let's look at an example. When we convert this one to be a series of nodes, this one, the Boolean of is n, will be false all the way to APPL. So all of them, the attribute of is n will be false until we have the last one, the last character, yi. The is n will be, the is n attribute will be true. So this is how we can tell the data structure to see which of the character is the end of the word, and the word. And then we have the trie class, and then the initialization, we just have a dummy node. We just create an object of the node with every of the attribute as a default. And then have the insert. We have the pointer of the node. So the initial pointer to be the self.node. So this is the root node, the root of all the root nodes. So this is the most root nodes. And for all the character in the word, if the children attribute of the list is not already exist. So if for that spot in the children list is none, and what we need to do is to create a new node for that character, and we use the ASCII system to convert the character to the numbers, and then we find a corresponding spot in that list. So for example, ORD8, so that is going to be in ASCII system, it is 61. And then the distance between the ASCII value for the character and the ASCII value of the small a will be where we can put the child node on that list. If the child has been created previously, we don't need to create it anymore. And then we update the pointer to be the children node, the child node by this statement, and then the for loop comes back again to look at the next character and the next one and next one. And then at the end, for the last character, we will update is n to be true because it is really pointing to the last character. So as this Boolean value points to the last one to see if that ends the word. And so this is the insert function. In terms of space complexity, will be the big O of M, because this is in the case where all the character has not been inserted previously. So it takes big O of M for each of the character that newly inserted. And this is the same for the time complexity. And it's very similar function between the search function and also the start with function. That's why I created a function named find. As you can see, both these functions call this function. Let's take a look at this find function. So the current node, the pointer node, we put in the root node at the beginning, and then you loop through all the character within that string. If that character is already in the child, we update the pointer. Otherwise, that means we couldn't find it. That's how we can return a false, meaning that we couldn't find this child, and then also return a self.node. So this is the root node. And in the success case, we will return a true, meaning that we already found it in the children, and then we will return the latest node as a tuple. And the reason why we use this tuple system is because the search and the star Swift they need different output from this find function. For the search, we need the last node. If the last node is end, meaning we capture the last character, meaning we capture the entire word, and this will take on this case. Otherwise, you take on this case, the self.node will be a false statement. If this is really the last character of a word, it will return the true in the isEnd attribute. For the stars with function, is a bit more straightforward. And for the stars with function, we just need the first part of the tuple output to see if that prefix has been found or not. So they have the same time complexity and also the space complexity. The time complexity is where the worst case will be where we have to check each character of the word or the prefix, and the space complexity is a big O one. This is so much about the solution. I hope you like it. If you do, please consider like this video and also subscribe to the channel. And thank you for watching. I'll see you next time.